Jnanam Paramam Dheyam. Knowledge is supreme.
We have taken a small holiday from spectroscopy to discuss something that many of us know already to some extent, and that is symmetry of molecules. And at this point, I cannot blame you if you are surprised and if you think that what is going on. Why is it that in a course of spectroscopy, all of a sudden we have started talking about symmetry point groups and stuff that we have studied in organic chemistry or inorganic chemistry? The reason why we are doing this is, as you are going to see in the next couple of months, symmetry plays a very important role in spectroscopy. So, what is the recurring question of the discussion we are having? The recurring question is, we have two wave functions, two states characterized by two wave functions. Can we or can we not get a transition between the two, right? That is the theme of the course. If you have to summarize the entire course in one sentence, then that would be it. Now, as far as diatomic molecules are concerned, we can do exact calculations and we can get at this, at the answer to this question exactly. When we go to polyatomic molecules, even when we go to electronic spectroscopy of diatomic molecules, it becomes apparent that the situation is such that if you ignore symmetry, then you really cannot go very far. And also, there are problems that become simpler if you consider symmetry. In fact, that is not the case only for spectroscopy. Even in quantum mechanics of molecules that you have studied things like Hartree-Fock theory and all that, right? Maybe you have studied, many of you, Huckel approximation, remember? So, you understand, I mean, suppose I want to work out the energy levels and spectra of something like say naphthalene. In Huckel theory, what have you learned? You get something, you get a determinant, don't you? What is the determinant called? Secular determinant. Okay. In case of Huckel, how big will the determinant be? So, sorry, what I was saying, so going senile. In case of naphthalene, how big will it be under Huckel approximation? Under any approximation, right? 10 by 10, right? 10 this side, 10 this side. Okay. You want to work with the determinant? I don't. That's too big for me. So, what you can do is, using symmetry, you can break down such determinants into smaller determinants, 2 by 2, maximum 3 by 3, and you can work with them. So, symmetry helps you simplify complicated quantum mechanical problems in general. In this course, what we will do is, we will focus on how symmetry plays a role in determining whether a transition takes place or not. So, even though we learn how to derive character tables, we will not ask questions on that, but we will ask questions, and that is the part you did here. We will ask questions on using character tables and also other concepts of symmetry that we develop now. Okay? That is the point. So, essentially, what is it that determines whether a transition takes place or not? By now you have, I hope, been convinced sufficiently that it is transition moment integral being non-zero. Okay? So, when I have a transition moment integral, I can write it in three, I can actually write it as a sum of 3, right? I will write the components of dipole moment, mu x or mu r mu z, work with one of them at a time, psi I integrated over all space. This integral has to be non-vanishing, right? This has to be non-zero. Okay? All right. Now, see, let us think of some wave functions, some easy wave functions that we know. Let us talk about, let us say, your old friend particle in a 1D box wave functions. Okay. I see that particle in a 1D box brings smiles to some faces, as we know, we have studied it in several different courses, haven't we. So, you know the wave functions, this is the first one, this is the second one, and you know how it goes. Okay. Now, particle in a box, as you know, is a model that works to certain extent for things like conjugated polyenes, right. So, actually it is a model that can be used in real chemical systems to some extent, not to a very large extent. Now, see, suppose I want to say that I have a particle in a box, this is my level 1, this is my level 2. Will the transition work or not work? Let us look at the symmetries of this. Do you see that this is an, what is it, odd function or even function? Even function, right. What is this? Odd function, that means if you change x to minus x, it will change. If you, it will change sign. If I think in another way, think of this point, if this is a center of inversion, if I take a conjugated polyene, right, then it will have a center of inversion. Then this is what? Symmetric with respect to inversion, this is antisymmetric with respect to inversion, right. I hope we all know the meaning of antisymmetric, symmetric and antisymmetric. Symmetric means does not change sign, antisymmetric means plus becomes minus, minus becomes plus. Okay. So, you agree that this is symmetric, this is antisymmetric. Okay. Suppose I consider mu x or mu y or mu z. So, they are like vectors along x or y or z. Are they symmetric or antisymmetric with respect to inversion? This is your center of inversion, this is plus, this is minus. What is inversion? Start from one point, go to the center, go to an equal distance on the other side, you should get the same thing back. What happens if you invert this arrow? This is what happens, right? Right. So, if I write this as some vector r, this is minus r, what is that okay or no? Alright. So, if I write it in the form of an equation, what do I get? I say r dash is the transformed vector is equal to minus r. Okay. So, see this operation that I have done, right, an inversion can be written in the form of an equation. Okay. That is what we are going to build upon in the next couple of days. Now, so it is antisymmetric, we agree. So, if I write it like this is equal to minus 1 multiplied by r. So, this now becomes I can to make things more interesting I can write like this. Let us say this is my inversion operator that operates on the vector r, that gives me minus 1 multiplied by r vector. Now, this is a form of equation that has been deeply ingrained in our minds by now. What kind of equation is this? It is an eigenvalue equation, isn't it? It is an eigenvalue equation. You have an operator, inversion operator operating on some function r, it gives you back the same function multiplied by an eigenvalue. Okay. Eigenvalue is minus 1. So, you can think like this also, that if the eigenvalue is minus 1, then it is antisymmetric. If the eigenvalue is plus 1, then it is symmetric. If the eigenvalue is something else, then it is something else. We will come to that something else later. Okay. So, now see, what is the eigenvalue for psi I? If this is psi I, this is psi f. Eigenvalue is 1 for psi I, for psi f minus 1, excellent. For mu x or mu y or mu z, what is the eigenvalue? No matter whether you take x or y or z, they will all look like these arrows, right? X will be like this, y will be like this, z will be like this, that is all, minus 1. So, you take the product of eigenvalues, what do you get? Minus 1 into minus 1 into plus 1, plus 1, right. That means the integrand does not change upon inversion. Okay. The integrand does not change sign upon inversion. However, if I draw one more, now let us say this is psi f dash. What is it? Is the eigenvalue plus 1 or minus 1? For this is plus 1. Symmetric, antisymmetric, symmetric, right. So, now see, now the integrand becomes antisymmetric. What does that mean? If you apply inversion, you take a molecule, take this conjugated polyene and invert it, integrand becomes minus 1. What happens to the integral then? Should the integral change? I have just inverted a molecule, should an allowed transition become a disallowed transition? No, right. So, what happens is if you take the value of the integral value cannot change. So, even though the integral value has become minus say I, okay, when before inversion let us say the value of the integral is I. After inversion of course, it will become minus I. So, what you get is that in this case I has to become minus I. When is I equal to minus I? Only when I is equal to 0. Is that right? Can you think of any other number whose negative is equal to itself? No, right. So, the point is this, when your integrand is symmetric with respect to a symmetry operation, then the integral survives. When it is antisymmetric, then it does not survive. Okay. We are going to come back to this. So, in case you have questions, hold on to them and we can revisit them when we discuss this in more detail. The reason why we did it is to just show you that symmetry can give you certain answers. So, the answer that I get here is that you cannot have a what is the lowest level, what is the quantum number, 0 or 1? 1. So, 1 to 2 transition is not allowed, 1 to 3 transition can be allowed. What about 1 to 4? Not allowed. 1 to 5 may be allowed. Okay. You can do the same thing with harmonic oscillator wave function. So, what you say is 0 to 1 is allowed, 0 to 2 is not allowed, right. So, you already get delta V equal to plus minus 1. Okay. So, you see, using symmetry you can arrive at the selection rule in a little simple fashion, but then of course, a simple fashion is usually a less accurate or less rigorous fashion also. So, from if you just use symmetry for simple harmonic oscillator for example, what you will end up saying is that 0 to 1 is allowed, 0 to 3 is allowed, 0 to 5 is allowed, right. You will never be able to say that only delta V equal to plus minus 1 is allowed. So far are we okay that if the integrand changes sign, then the integral has to be 0, right. That means, in order for the integral to survive, your integral must be symmetric with respect to, so far we have discussed only inversion. Okay. Now, what we are trying to say is this, think of a harmonic oscillator wave function. From this argument we can say that this 0 to 1 transition is allowed, because 0 wave function looks more or well at least qualitatively like this, 1 wave function is like this. So, this is symmetric, this is antisymmetric, 2 is also qualitatively like this. So, I can say that for a harmonic oscillator 0 to 1 is allowed, 0 to 2 is not allowed. But if I use only symmetry argument, I will end up saying that 0 to 3 is also allowed. Understand what I am saying? So, but actually it is not. Only delta V equal to plus minus 1 is allowed, that is what we have derived already. So, using symmetry you can usually get a good hint about which transitions will be allowed, but eventually you have to do the quantum mechanics also. But symmetry helps us simplify complex problems, that is it, that is why we will study it. So, what we have to do now is this, the way we discussed very briefly in the previous day is we introduce symmetry operations, symmetry elements, symmetry point groups, and in case you need to revise a little bit about that, what you could do is you could of course read Cotton's Symmetry in Chemistry book, first chapter or first couple of chapters. Now, what we will do is this, so far we have presented the problem to you as a geometry problem, okay. But then as we have written here, it is not very difficult to convert this problem in geometry to a problem in algebra. And if you want to develop a systematic way of using symmetry to solve problems in spectroscopy or quantum mechanics, then it is going to be more convenient if you write this in the language of algebra. Because finally what we want to do is When you go to big molecules and all, we do not want to do anything ourselves, it gets too tedious. We want to ask a computer to do it. Okay. Computer is blind and deaf. The only thing it understands is numbers. Well, that also in a special form. So, we try to convert everything to numbers, and the way in which we go from the domain of geometry to the domain of algebra is by using what are called transformation matrices. So, what we will do is we will try and write a matrix for each and every symmetry operation. Okay. Let us try to do that, then we will get into something called representations. Okay. So, in order to do this, so here what did we do? We tried out our symmetry operation on a vector, right, R. So, in this case R is called the basis. The function or set of functions on which you make your operator operate is called the basis. And as we will see, using a basis that is of relevance to us, we can try to construct the transformation matrices. Okay. Let us try doing that. Initially, let us do some very generic examples, then we will get into some point groups. Okay. Let us start with a simple basis, x, y, z, but I want the entire board. Let us say I am using the basis x, y, z. I want to see how x, y, z, the coordinates, transform in response to different symmetry operations. Are we clear? Are we clear what the basis is? Are we clear what is the meaning of basis? And are we clear what we are trying to do? If not, this is the time to ask. Yes. Remember, so question is explain this concept of basis once more. You take some function phi, you make some symmetry operation operate on it, you get some transform function, okay, and we are going to well, let us say we get it an eigenvalue equation something like this, we get something like f into phi. Okay. So, what we are saying is this function forms the basis for the discussion of this symmetry operation. Sometimes one function is not enough, like here I want to see how the coordinates transform. I could take them separately, but as you will see a little later, for certain functions you cannot take them separately. So, then what we do is instead of taking one function, I take an array of function, write them as a row vector or a column vector. Have we understood what basis is? Basis is a function or set of functions on which our symmetry operations are being made to operate. Are we clear about that? Okay. Now, let me write these are the transform functions x dash, y dash, z dash. Okay. And let me now select my symmetry operation. Okay. When we learn tables, what is the table we started with? Multiplication table, very easy question. When you are kids, small children, when we learned multiplication table, we started with the table of 29.32, isn't it? What was the first table we learned? Yes? 2, right? Actually 10 would be easier. Okay? So, if you are even lesser mortal, you would start with the table of 1. At 0 to everything is 0, why do you multiply? 1. So, what we will do here is that we will start this seemingly complicated discussion with the simplest possible multiplication by 1. What is 1 in symmetry? Which operation is that? Identity operation, right? Identity, or you can say C1. C1 means rotating by 360 degrees, or in other words doing nothing. Okay? So, if it was addition it would be 0, multiplication it is 1. So, let us say E. So, if E operates on x, what is x dash? X. If E operates on y, what is y dash? What is it? When E operates on Z, what is that? See, you better answer now when it is easy, later it will get complicated. So, if this is the case, then I think it is not very difficult for you to understand that instead of the operator, I might as well write a matrix. What is a matrix I will write? Unit matrix 1 0 0 0 1 0 0 0 1, very simple. So, what we are saying is under the operation of E, each of the coordinates remain unchanged. So, another way of putting it would be that each of these coordinates x, y and z are symmetric with respect to the operation E. And at this point, if you think that the discussion that we are making is trivial, then I am with you. I agree with you, the discussion is trivial. The only reason why we are saying it is to kind of get into the subject. Have you all understood this, or is there a question? No question? Very good. Now, let me try something else. Let me try say sigma zx. X, y, z. Sigma zx will have its own transformation matrix that will give me x dash, y dash, z dash. I am not writing now. So, what tell me? You want me to draw it? X, y, z. Okay. So, what I am doing is I have taken some point here, coordinates are say x, or you can write x1, y1, z1 also if it is more comfortable for you, it does not matter. How will they transform? I am reflecting with respect to the plane zx, that is the plane of the board. X, what will x become? X remains x. What will z become? Yes, z becomes z. And what will y become? Minus y. Alright. What is the matrix? 1 0 0, 0 minus 1 0, 0 0 1. So, almost the same as the unit matrix, with the difference that one of the coordinates is actually antisymmetric. So, what do we see? X is symmetric, z is symmetric with respect to sigma x z, y is antisymmetric. Okay. How would this matrix change if I wanted to write it for say sigma y z? Yes, sigma y z, maybe I will write it here. What are the coordinates that would change sign? What are the coordinates that would not change sign? X changes sign. What about y and z? Same. So, matrix will be what? Minus 1 0 0, 0 1 0, 0 0 1. And if it is xz, if it is xy, reflection with respect to xy, z changes sign and x and y do not. So, it will be 1 0 0, 0 1 0, 0 0 minus 1. That minus sign just goes down the diagonal, that is all. Okay.